That report for industrial technology is due next week. How am I going to get it done? Hey, I know. I'll see what my computer can do. Oh, computer.
Yes, Karen?
Oh, come on. Use your human voice.
Oh, you mean this, Karen?
Yeah. Hey, I've got a problem. My report on construction technology is due next week, and...
And you thought I could write it for you, huh?
Well, no. I'm just not sure where to start.
How about if you began by giving the definition of construction?
It's when you build a house or something.
Well, to be more precise, construction involves the system of people using tools, resources, and processes to make structures.
Man, that's a mouthful. But where do I go from there?
Well, what do you think is the first step in putting up a structure?
Buying all the materials you need?
Actually, the construction process usually begins with an architectural firm meeting with the client, which is another name for the people who have requested a building plan. During this meeting, the architectural firm finds out what type of construction the client is interested in, whether it's building construction or civil construction. Building construction includes structures like houses, office buildings, stores, and factories.
Yeah, but what's civil construction?
Civil construction involves roadways, like streets, and highways, as well as more complex structures, like bridges and sewage treatment facilities. Now, the firms that create these projects often consist of both architects and engineers.
Architects draw up plans, don't they?
That's right, while engineers concentrate on the details, like the size of the beams, the exact materials that will be used, and so on. Then, after the architects and engineers understand their clients' needs and desires, they have surveyors prepare a survey of the site. A survey shows everything on the site, including boundary lines, slopes in the land, and the location of existing greenery or structures. With this information, architects and engineers come up with a few thumbnail sketches.
What are thumbnail sketches?
They are very small drawings that allow architects to quickly rough out a few designs, like these. Eventually, the architects select their favorite sketch.
How do they know which one to pick?
Well, along with selecting a layout that looks attractive and meets the needs of the client, an architectural firm must make sure that the design meets a number of regulations. These include zoning laws, building codes, and local covenants. Do you know what any of these are?
Yeah, zoning laws tell you what type of building you can put up, right?
That's pretty close. Zoning laws regulate how many people or structures can be located in a given area of land, as well as the types of structures that can be built there. For example, commercial zones are intended specifically for structures like malls, restaurants, and grocery stores. Industrial zones, on the other hand, are for structures like factories and warehouses. Now, what sort of structures do you think are allowed in residential zones?
Oh, I know, houses.
Right. Houses, apartments, condominiums, and other residential buildings. Another category of regulations that can affect the construction of a building are building codes. These are guidelines for how a structure should be built, along with the quality of the materials being used. They're enforced by local building inspectors who may visit a site several times throughout its construction to make sure it's meeting all the necessary safety requirements. Building codes also apply to structures like dams, bridges, and highways. To give you an idea of what I mean, many highway overpasses, like this one, must have enough clearance for large vehicles to go under them, and also be strong enough for those same vehicles to go over them. Communities may also have local covenants.
Covenants?
Yes, these are often ordinances that regulate the size and style of structures that can be built in a community. Some covenants also specify the types of trees or shrubs that can be planted.
Boy, they're pretty picky.
Well, actually, covenants are meant to preserve the style of a neighborhood while protecting its market value.
Oh, okay.
Once an overall plan has been agreed upon by the firm, the architects and engineers design a series of detailed renderings.
Then do they start building?
No, there are other elements to the designing and engineering process, including getting client approval and selecting the general contractors who will assign people to do the construction work.
Boy, it takes a lot of people to build a house.
That's right, Karen. And there's another step that takes place before any construction is done.
What's that?
That's part of what is known as site preparation. All told, there are 3 elements to site preparation: removing unnecessary objects like rocks and existing structures, as well as leveling the plot and locating where the structure will go.
Wow, that's a lot of work.
It sure is. Preparing a site for construction takes the efforts of professionals like surveyors and operating engineers, as well as special tools, including earth movers.
Like bulldozers.
Exactly. And to determine the location of the structure, surveyors use tools like leveling rods and transits.
Well, everything I've heard so far sounds okay, but my teacher also wants me to talk about how buildings are put together.
Well, first you have to realize that there are 2 parts to any type of structure: the substructure and the superstructure.
What are those?
Basically, the substructure is the foundation system that not only supports the weight of the main structure, but distributes this weight over a large area. Now, the main structure, also known as the superstructure,
That's the rest of the building, right?
yes, the superstructure is what rests on top of the foundation. In all, there are 3 different kinds of substructures: slab foundations, spread foundations, and pile foundations.
How do architects know which type of foundation to put in?
They consider a number of elements: the type of structure, the type of soil, and the climate in which they're building. Slab foundations are best for small, lightweight structures where the soil is soft or has a lot of groundwater. One type of slab foundation is called a floating slab because it sits directly on top of the earth. Because of this, floating slabs aren't often used in certain areas of the country where the ground freezes in winter. You see, when soil freezes and thaws, it shifts and moves. So a slab foundation built on this type of ground would simply move along with it.
What about bigger buildings?
Well, depending on the soil, larger, heavier structures tend to be supported by either spread or pile foundations. If the soil is hard or near bedrock, a major structure may be built on a spread foundation, which places the weight of the structure on thick support walls. And depending on the depth of these walls, the space they create may serve as either a basement or a crawl space. However, in climates where the ground freezes in winter, they must be set below the frost line so that they won't shift when the ground shifts. But for structures like bridges, where the soil is wet or sandy, pile foundations are often used. On these, piles or posts are driven into the ground until they reach solid soil or bedrock. This keeps them from moving or shifting. Footings are then attached to the top of the piles.
I didn't realize all that work went into just putting in the foundation.
Well, it's important to construct a solid foundation so that the superstructure above it will be sturdy too. But along with there being different types of substructures, there are also a variety of superstructures. These include minor superstructures, major superstructures, and alternative superstructures, like geodesic domes.
Geo what?
Have you heard of the Epcot Center at Walt Disney World Resort?
Oh, yeah.
Well, it has a geodesic dome known as the Spaceship Earth. A geodesic dome uses a series of triangles to frame its outside shape. These triangles give the structure a lot of compression strength and transfer all the weight to the outside walls. That's why most geodesic domes don't have interior support beams or posts.
Hey, you're right. I never realized that.
But for factories, houses, and other traditional superstructures, supports are needed for framing and shaping. In minor structures like houses, studs, joists, and trusses are used to form the exterior walls, subfloors, interior partitions, and the roof. But in major superstructures, like this office building, steel pillars and beams are used because they have the strength to support multi-story structures.
I think I've got that. But what about highways?
Highways and dams require massive amounts of either dirt, concrete, or stone. Take the Hoover Dam. It was made with large amounts of reinforced concrete. This allows it to contain the 30.5 million acre-feet of water in Lake Mead, the lake constructed for this project.
Man, what do they do with all that water?
It's used to irrigate thousands of square miles of farmland. And the dam generates enough energy to support most of the southwestern United States. Now, once the substructure and the superstructure have been completed, what do you think is the next procedure?
Well, I guess you put up the walls.
Actually, you're forgetting a few things that make a structure more comfortable.
Like what?
Utilities.
Oh, you mean plumbing and stuff?
Yes. Water and sewer systems are two examples of utilities. Electrical systems are another essential utility installed on most structures. After all, without electrical systems, you wouldn't be able to talk to me right now.
Hey, where'd you go?
Just kidding. Where was I? Oh, and without electricity, your house could get pretty hot in the summer and a little cool in the winter.
Well, I get why we need utilities, but why are they put in before the house is finished?
Because the walls and ceilings need to be open so that there is space to install air ducts for the heating and cooling, the wires for the electrical systems, and the pipes for the water and sewer systems. Then later, when the walls, ceilings, and floors are covered, the right fixtures, switches, and appliances can be installed.
Great. Now, when do you start painting and carpeting and...
Those are part of the enclosing and finishing phase of construction, which transforms an unfinished structure into a shelter. Shelters offer protection from rain and other bad weather, as well as from intruders. And in earlier times, they offered protection from predators. Other reasons for enclosing and finishing a structure include comfort and convenience. The structure's exterior is enclosed first, including the exterior roof, walls, windows, doors, and skylights. The interior is enclosed in much the same way. Interior walls are often covered with a material called drywall. The drywall may then be covered with paint, wood paneling, wallpaper, or one of many other materials. Floors are covered too, with materials like vinyl, carpeting, and wood.
So, is the project done yet?
No, the finishing process also includes adding trim to the interior and exterior of the house, as well as installing accessories. Some bathroom and kitchen accessories include cabinets, faucets, shelving, and light fixtures. Accessories must also be added to civil structures. Highways, for example, need accessories like pavement striping, guardrails, reflectors, and signs. Also, finishing is usually done to the plot or land surrounding the structure, which may include constructing pathways.
Like a sidewalk.
Yes, sidewalks and driveways. In addition, commercial and industrial sites may also have parking lots. Landscaping is another element of finishing a site. This can include planting trees, grass, and other greenery. The last step in finishing a structure involves giving final inspections, paying all materials suppliers, and having subcontractors and suppliers sign work releases. With that completed, the general contractor collects the owner's final payments and then transfers the responsibility of the project to the owner.
You know, you've been a lot of help. I'll have to talk to you when I get to my other industrial technology projects.
What other projects?
See you later, computer.
Oh, brother.
To someone who's only bought and used 2x4s, 2x6s, and 4x4s, buying hardwood becomes a challenge. But there's nothing mysterious or difficult about buying and using hardwood. It's just different. One might ask, why didn't all the mills get together and decide on uniform sizes? The answer is they could have, but that wouldn't have been of very much help. You see, hardwood and softwood are used primarily for two different types of construction. For the most part, softwood is used for building construction, and hardwood is used to make beautiful furniture and do finish work. The end uses of the lumber are essentially different. So what's the difference between hardwood and softwood? The first thing we must understand is that the names hardwood and softwood do not mean that hardwood is harder than softwood. There are some species of hardwood that are softer than softwood, and some species of softwood that are harder than some species of hardwood. Got that? So what's the difference? First, hardwood comes from trees that are broad-leaf deciduous, meaning they shed their leaves every year. And softwood comes from trees that are cone-bearing, coniferous, needle-leaf trees, most of which are evergreen, meaning they retain some of their needles all year long. Beauty is hard to define, but hardwood has that look, and that appeals to our sense of beauty. But beauty is not the only reason hardwood is used almost exclusively for furniture and other fine products where wood is the dominant feature. There is a biological difference between hardwood and softwood. Hardwood is more dense. The cellular structure of hardwoods is more complex than that of softwoods. The millions of tiny cells that make up the wood are packed more tightly together in hardwoods. The cell walls are thicker, which makes the wood denser, heavier, and generally stronger. Another difference is the presence of axial vessels. These aid in the conduction of water and soluble substance throughout the tree. These support cells add more strength. Hardwood makes up 60% of the world's forest. Its variety of color and grain patterns, coupled with its inherent strength, make it the ideal furniture wood. But each hardwood species has its own set of unique characteristics, and therefore often their own special applications. For example, walnut is prized for use in gun stocks. Ash is good in sporting equipment, such as this bat, while white oak makes leak-proof barrels. We all find it easy to fall in love with the warmth and beauty of furniture, cabinetry, and other items made from genuine hardwoods. But are we taking it for granted that our desire for this beautiful wood is environmentally sensitive? The fact is that hardwood, because it is a product of nature, is one of our few renewable natural resources. Properly managed, North America's hardwood forests can provide to future generations the beautiful hardwoods we've come to appreciate and can provide it forever. There are 728 million acres of forests in the United States. That's 1/3 of the land area. And that's 70% of the amount of land that was forested when Columbus landed 500 years ago. Of this, 476 million acres is true commercial forest, capable of growing a significant amount of timber and is not withdrawn from production by statute or regulation, as the national parks are. Trees in a commercial forest are really no different than any other agricultural crop. They just grow much larger and require a longer time before harvest, years instead of months. In the United States, more timber is growing now than at any time in this century. Hardwoods are in every sense our renewable natural resource. Let's look at the cross-section of a tree trunk to see how it grows and what its parts are. A tree will grow in size at the tips of its branches, and by the addition of growth increments, or more commonly called annual rings, to the main trunk and limb. All of us have tried to determine the age of a tree by counting the rings. Historians can date wooden structures by comparing the relationship of the rings in the wooden part of the building to the rings in trees that are still alive growing nearby. A record of each year's weather is written in the growth rings. At the very center of the tree is the pith. It represents primary growth formed when the stems or branches elongate. It is generally darker in color and softer than the surrounding wood. Most branches originate at the pith, and their bases are intergrown with the wood of the trunk as long as they are alive. On the outside of the tree is the bark, a protective layer completely covering the living tissues of a tree. This layer, called the cambium, is a thin area of actively dividing cells that produce the tree's growth. As the cambium cells divide, those on the outside of the layer change and become the phloem tissue, conducting food downward. This is also called the inner bark. Cells to the inside of the cambium form the xylem tissue that conducts water and stored nutrients upward from the roots. Xylem tissue is what we know of as wood. Growth in the cambium layer produces bark on the outside and wood on the inside. New xylem tissue called sapwood is produced each year. Its function is to conduct water throughout the tree. The wood that is formed during the first part of the growing season is generally lighter in color and is called the spring wood. Late wood, formed after the early wood, is called summer wood. It is generally darker in color and more dense than the early wood. Each year the spring wood and the summer wood together form an annual growth ring. This can be seen by turning a board on end. Toward the center of the tree is the heartwood. It provides the support that holds the tree up. Heartwood is the structural framework of the tree. Now, very seldom is the heartwood shaped in the form of a heart like this. If you look very carefully, you will even see the arrow going through this heartwood. And some species of hardwood do not have true heartwood. Heartwood is formed when living cells in the sapwood die, when the energy-storing materials are depleted, and the cell walls are impregnated with protective materials. This process often produces a color change which greatly influences the value of the logs and the lumber. The appearance of lumber is affected not only by the wood structure, but also by how boards are sawn from the logs. Most lumber produced today is cut along the face of the log. This is called plane or flat sawed, or sawing around the log. Flat sawn lumber has this characteristic U or V-shaped pattern. Many people call this a cathedral pattern or a Gothic arch turned upside down. Quarter sawn or rift sawn lumber is cut on a radius from the pith to the bark. Lumber cut this way looks like this. Since quarter sawn lumber results in a substantial waste, little is produced today and the cost is higher than plain sawn. But quarter sawn lumber wears more evenly and has other advantages that might make it worth the extra cost to you. As a tree matures, various defects can result from natural growth characteristics such as limbs as well as other outside influences. Bark pockets are small patches of bark that have become a part of the wood as a result of injury or different parts of the tree growing together. Shake is the separation of wood along weak lines of cleavage. It may develop in standing trees or it may occur during the drying process. As a result of injury or insect attack, some trees, most notably cherry, develop gum-like deposits. This walnut tree shows birdpeck, arranged in a horizontal tier encircling the trunk. Birdpeck usually shows up as small bark-filled pockets 1/4 to 1/2 inch in diameter, surrounded by distorted grain. Insects called wood borers do tremendous damage to both standing trees and cut logs and lumber. Besides the physical damage from the holes, which can be up to 1.5 inches in diameter and 10 inches long, the borer infestations also provide a means for decay fungi to enter the tree and cause additional damage. And finally, stain is a general term used in the lumber industry that refers to the discoloration of wood. Stain can happen naturally in living trees or can be the result of improper handling of logs or lumber. All the factors that we've just talked about affect the grading of hardwood. The grading of lumber is a means of measuring its quality, which is directly related to its price. The concept is simple. A high-grade board must have more clear, defect-free surface area than a low-grade board. With some exceptions, hardwood lumber is graded on the basis of the size and number of cuttings or pieces which can be obtained from the board when it is cut up and used in the manufacture of a hardwood product, such as furniture, flooring, or interior house trim. Common usage generally requires that the cuttings be clear wood, so that the undesirable defects do not appear in the finished product. Generally speaking, the higher the grade, the larger area of clear material contained in an individual board. The National Hardwood Lumber Association was formed in 1898 to establish uniform rules for the inspection and grading of hardwood lumber. They set the standards. They have also established a school to train hardwood lumber inspectors. The National Inspection Service serves as the final authority on the application of grades throughout North America. An important fact to be remembered is that the experienced grader will grade a board according to how it will finish out at the standard surface thickness. So if a board has a stain or other defect that will not be present once the board is planed to its finished thickness, the defect will not be counted in the grading. The standard grades of hardwood lumber, starting with the best, are first and seconds, written as FAS. Then come selects, number 1 common, number 2 common, and finally number 3 common, which is used primarily for pallet boards and shipping crates. To understand how a board is graded, let's follow this board through the grading process. First, the inspector determines the species, but generally a mill processes only one species at a time, so that's not difficult. Next, by using the board rule, the inspector determines the surface measure. Then the poor side of the board is picked. The grade is almost always determined from the poor side of the board. A trial grade is given to the board. Remember, boards aren't graded by their overall appearance. It is assumed that the user of the board wants clear lumber to work with, and so a piece of lumber is graded according to how much and what sizes of clear lumber can be obtained from any particular board. Since each grade demands a certain number of cuttings, the inspector will try to get that number out of the board. The inspector must also determine the minimum size of the clear face cuttings needed to maintain a trial grade. In this illustration, the inspector is marking the board so we can visualize what is going on. In actual practice, this is done in the head of the inspector. Two boards that are exactly the same size with the same number of cuttings and the same amount of defect-free surface area could end up with different grades because of the location of the defects could prevent a board from having large enough clear cuttings to make the higher grade. The figures are calculated. If a board does not yield sufficient clear face cuttings units of the right size and number of cuttings, the inspector tries the next lower grade. A cutting unit is 1 inch wide by 1 foot long. A cutting must be obtained by cross-cutting, ripping, or both. It cannot be obtained by diagonal cutting the board. This board contains 70 cutting units and the minimum size of clear face cuttings to give it a grade of 1 common. For more information, please call or write to the National Hardwood Lumber Association. Their address is Post Office Box 34518, Memphis, Tennessee 38184-0518, or call them at area code 901-377-1818. If you have a fax, they can be reached at 901 382-6419.
Let's travel to the Georgia Pacific Corporation plant in Emporia, Virginia, where over 240 million square feet of plywood is manufactured every year. Specialty products such as exterior siding and floor underlayment are also manufactured here. Incoming truckloads of logs are first weighed. The volume of material required for plant operation prevents purchasing logs by measuring or scaling them, so purchases are made on a weight basis. The principal species used in the manufacture of construction and structural plywood at this plant is southern yellow pine, but the manufacturing standards of the American Plywood Association classify over 70 species of deciduous and coniferous trees which can be employed in the manufacturing process. There are 5 levels or groups. Group 1 species are the strongest and include species such as American beech, birch, sugar maple, and southern pine. Group 5, the least strong, includes basswood and balsam poplar. Large forklifts, which are able to unload an entire truckload of logs in one lift, speed the process, minimizing time lost in unloading. Loads of logs are identified as to logging site or contractor, and scalers spot check incoming loads to ensure that plant standards for length, diameter, and log quality are being met. The plant utilizes better quality logs in order to maximize the yield of high-quality veneer. Logs are sorted at the logging site, with smaller and lower quality logs diverted to the production of other products based on wood fiber, such as oriented strand board. The logs on this deck and those being processed are yellow poplar, a Group 2 hardwood possessing good strength and stiffness qualities. The first step in the process is debarking. Here, a ring-type debarker, using rotating cutters, quickly removes the log's bark with its embedded dirt. This style of debarker is very quick and efficient. The biggest drawback is the diameter size limit it places on logs passing through it. After debarking, the logs pass through a deck saw where ends are trimmed and the logs are cut to 104-inch lengths. The trim from the saws, as well as the bark, is used as fuel in a waste-fired steam boiler. The logs, now called bolts, are conveyed to a hot water bath where they are soaked for 4 hours at 200 degrees. The process softens the wood fibers, producing high-quality veneer. A chain conveyor slowly moves them through the bath to a conveyor which brings them to the lathe. The rotary lathe charger in this plant is computer controlled. The bolt is brought to the charger, which grips the ends in their geometric center and turns the bolt one complete revolution. As the bolt revolves, it is scanned, and the charger is adjusted to maximize the veneer yield. The bolt is then passed to the lathe, where chucks grip the bolt ends and transmit torque to turn the bolt against the lathe knife. As the bolt revolves against the knife, it is automatically fed into the knife to produce a continuous ribbon of veneer. As the bolt is reduced in diameter, a backup roll is lowered to the back of the bolt to stabilize it. When the bolt diameter has decreased to about 5 inches, the core is automatically ejected and the next bolt is brought up. The cores are conveyed to racks where they are accumulated for shipment to other plants, where they may be sawn into 2x4s, manufactured into landscape ties, or chipped for use in the manufacture of paper or other wood fiber products. The early veneer, termed fishtails or roundup, is either diverted from the production line to be used as fuel or in the manufacture of other wood fiber products, or if the amount of usable veneer is sufficient, it is pulled from the line to be hand-trimmed and used as core stock or crossbands. The stream of veneer passes under a clipper controlled by an optical scanner which cuts out defective areas and cuts the veneer into standard lengths, usually 54 inches. Full-length pieces to be used in plywood faces and backs are automatically diverted to an overhead conveyor and storage racks. Random width narrow pieces and pieces requiring further hand trimming are pulled from the conveyor into bins to be used in the inner plies in the panels. Fishtails or roundup veneer are sorted and hand trimmed to obtain as much usable veneer from each log as possible. The smaller pieces are used in the inner plies of plywood panels, termed crossbands. After clipping, trimming, and sorting, the packages of green veneer are routed to the veneer dryer. The dryer maintains a hot, humid atmosphere in which the veneer gives up moisture. The veneer spends about 9 minutes in its journey through the dryer, beginning at a moisture content as high as 60 to 70%, emerging at a moisture content of about 5%. While most of the veneer is dried to specification, all the veneer passes under a moisture content monitor. Any veneer exceeding moisture content limits is automatically marked with a red line and is pulled into a bin for re-drying. As the dried veneer moves along, it is graded and pulled from the line and placed on piles of similarly graded veneer. Veneer sheets can be upgraded for use as faces and backs by patching. This machine punches out the defective area and replaces the defect with a patch called a boat patch in one operation. After the veneer has been dried and sorted by size and by grade, it is taken to the layup line. A full-size panel back is first placed on the conveyor. It passes under a spray head, which lays down a coat of phenyl formaldehyde resin. A crossband of narrow random width stock is laid down next, with the wood grain at right angles to the bottom sheet. Adhesive is sprayed on the crossbands, and the core ply is placed over the bands with the grain of the core parallel to the back ply and at right angles to the crossband ply. Glue is again applied, a crossband layer is laid down, adhesive applied, and the outer ply is laid down, completing a rough 5-ply, 5-layer panel. A saw clamps the panel and cuts between face and back sheets to separate any crossband pieces which are shared between adjacent panels. The rough, oversized panel is then conveyed to a pre-press, which employs pressure but no heat, to form an initial panel bond. This minimizes shifting of panel plies in the loading of the plywood hot press. After pre-pressing, the panels are loaded into a hot press where the panels are subjected to temperatures of 300 to 330 degrees and pressures of 300 pounds per square inch for about 30 minutes, depending on the number of plies and panel thicknesses. The press opens after the panels have cured under heat and pressure, and the rough panels are automatically pulled onto an elevator. The stack of panels, called a hot stack, is removed from the elevator conveyor and set aside to further cure and cool. After cooling, the panels are trimmed to a standard size, such as 4 by 8 feet. The trimmings are pulverized and used as boiler fuel. The panels then pass a grading station where each panel is graded front and back and routed to the proper bin by the grader. The panel dimensions are constantly spot checked to ensure they are within APA limits. As part of the grading process, certain panels which can be upgraded by patching with a synthetic material are identified. These are patched, the patch is cured by ultraviolet light, and the panels are then sanded to produce a high-quality surface. Sanded panels, usually higher quality, pass another grading station to be graded, grade marked, and sorted into appropriate stacks to be packaged and placed in inventory. We have seen how both the veneer and the final plywood panels are produced in the softwood plywood industry. Let's journey to Erath, Curry, and Morrow Associates in Rocky Mount, Virginia, to see how hardwood veneers, important to the furniture and cabinetry industries and widely used in interior decorative paneling, are produced. Logs being held in inventory are kept under a water spray to minimize end checking and surface checking. Logs entering production first pass through a debarker. In this case, the debarker is a type known as a Rosser head debarker. One of its advantages is its ability to debark logs of large diameter, often used in veneer manufacture. It is considerably slower than other types of debarkers, but speed is of less importance than the maintenance of high quality and high yield. Hardwood veneer logs and veneer are both very valuable. This plant employs a bandsaw to break down the debarked logs into half-log or quarter-log flitches. Slabs are first removed to produce a squared-up log. The log is then sawn into halves or quarters. The heart center of the tree, where defects tend to be the largest and most numerous, is the dark streak in the center of the half log, now termed a half-log flitch. Inventory information is marked on each flitch, and a tag carrying an identification number is attached to the end of the flitch. The flitches are conveyed to soaking vats, where flitches are held in hot water soak for a matter of hours to several days, depending upon season of the year, size, and species of the log from which the flitch was sawn. Flitches emerge from the vats at a temperature of about 190 degrees. The soaking process softens the wood fibers and produces superior veneer. By minimizing checks and splitting, the usefulness and value of the veneer is maximized. The flitches entering the plant have all remaining bark removed and are end trimmed to a specific length. They are then conveyed to either the vertical slicer or the stay log lathe. Let's follow a flitch to the stay log lathe. The log is prepared for the lathe chuck by machining two parallel grooves the full length of the log using two saw heads very similar to dado heads. When the flitch is placed on the lathe chuck grips the spine between the two grooves. On a stay log lathe, the flitch travels in an eccentric arc, with the knife cutting the veneer in an arc greater than the arc of the flitch's annual growth rings. This produces a type of veneer termed rift cut or comb cut. Since the flitch's outer face is not parallel to the lathe knife initially, The early veneer is not the full length or full width of the flitch. The smaller pieces are discarded. When the flitch has been trued up, the veneer comes off in full-size pieces. Veneer thicknesses range from 1/8 inch down to 1/100th of an inch. 1/85th is a common thickness. The flitch is automatically advanced into the knife until only a thin heartboard remains, which is discarded. Flitches are gripped by chucks on a vertical slicer. The slicer produces a piece of veneer on each downward stroke into a razor-sharp knife. The veneer cut first is again discarded until sheets of usable size and quality are sliced. These slices are so thin, they tend to curl. The heating and soaking process makes the thin veneer very flexible. The veneer resulting from a flitch is piled as a unit, tagged, and kept together. This allows matching for color and grain by the end user. The veneer, flitch by flitch, is put through a dryer about 100 feet in length. Depending upon wood species and veneer thickness, the trip can take from 1 to 17 minutes. The temperature and relative humidity within the dryer are closely controlled to produce veneer within a moisture content of 5 to 7%. The dried veneer is carefully piled into a package containing one flitch. Spot checks for moisture content and drying quality are constantly made. Occasionally, veneer will emerge from the dryer with a wrinkled appearance. This veneer is hot pressed before packaging. Various species and thicknesses are carefully packaged and held in inventory, awaiting sale and shipment. A sample room contains samples taken from flitch packages in inventory. Each package is represented by one or more samples which buyers examine in deciding on a purchase. The information on this piece of cherry veneer shows that the length of the veneer is 12 feet 10 inches. It was produced from flitch number 58357, that there are 3 samples in this set, with this sample number 1, and that there are 2,925 square feet of veneer in this package produced from a 1/2 log flitch. Some samples will show evidence of clipping to remove the heart center of the flitch, where defects and the poorest quality wood are present. Most hardwood veneer is produced on rotary lathes in a manner very similar to the production of softwood veneer. There are differences, however, due to the value of the raw material and the uses of the hardwood veneer. Let's travel to Tupper Lake, New York, to the Tupper Lake Veneer Division of Rutland Plywood to see how rotary hardwood veneer is made. At Tupper Lake, the logs are first placed in steaming chambers rather than a hot water soak. After steaming, the logs are debarked using a Rother head debarker. After debarking, the logs are conveyed through a deck saw, where they are cut to bolts of standard length. Upon entering the mill, the bolts are sorted by length and loaded onto an infeed deck, leading to the lathe charger and rotary lathe. The bolts are transferred from the deck to the lathe chucks by the charger and are turned to a core of about 5 inches. Hardwoods, such as hard maple and beech, are considerably harder to peel than softwoods and require a slower rate of feed. 2-stage chucks are commonly used, with the larger outer diameter retracting after the log diameter is reduced, to allow the peeling of the log to a smaller core diameter. The early Roundup veneer is riddled with defects, such as holes and tears resulting from debarking. Since the log is not a perfect cylinder initially, the veneer is not continuous or full width. The early Roundup is diverted into a chipper for use as fuel or in paper manufacturing. Once satisfactory veneer is being produced, it passes through a computer-controlled optical scanner and clipper, which cuts out open defects above a specific size and cuts the continuous sheet into standard lengths. Trimmed narrower material is cut into random lengths. The standard and random lengths of usable veneer are sorted and removed from the production line. The veneer thickness is constantly monitored as part of quality control. The sheets of hardwood veneer are carefully dried to a moisture content of 5 to 7%. Smaller, high-quality pieces of veneer are hand-clipped from sheets containing defects after drying. After drying, narrow pieces are carefully trimmed to standard sizes and coated with the urea formaldehyde resin glue. The adhesive is heat-activated and cured. These narrow pieces will be edge-glued to form larger panels. After trimming and glue application, the packages of veneer are taken to a splicing room where the sheets are edge-glued in a splicing machine. Several edge-glued panels can be joined to produce wider stock. Pieces of lower grade veneer used as core stock are joined using paper tape. The hardwood veneer production of Tupper Lake is intended primarily for the specialty hardwood plywood market, such as furniture and cabinet pieces and automobile and sporting good uses, rather than hardwood wall paneling. Let's travel from Tupper Lake westward across New York State to Jamestown, New York, home of the Jamestown Plywood Corporation, manufacturers of specialty hardwood plywoods. Veneer entering production at Jamestown is first cut to whatever length production requires. Trimmed material, called shorts, is carefully measured, marked, and inventoried for eventual use where possible. Since sliced veneer rarely has parallel long edges, the sheets of veneer are trimmed to obtain parallel edges and appropriate widths. The veneer strips are joined into wider panels, a heat-activated glue is applied, and the pieces are then edge-glued in a splicing machine. If splits are detected in veneer pieces being prepared, the veneer back is strengthened with a very thin paper tape. The veneer face is then carefully worked with an air hammer to close and conceal the split. Hardwood plywood can be manufactured with a lumber core, a particle board core, or a veneer core. In lumber core plywood, the material for the lumber core is first planed, ripped to width in a straight line rip saw, and then cross-cut to length, removing defects. The cut-up stock is run across a glue roll, which applies a layer of glue to one edge. The pieces are then laid up and run through a radio frequency hot press where the strips are joined under heat and pressure. When the lumber core emerges from the RF press, the strips are joined, but the panel will be put through an abrasive planer to remove glue extrusions and to obtain a satisfactory surface for veneering. This damaged panel had excessive moisture content in a damaged piece, which created a hot spot in the radio frequency press. The abrasive planer reduces panels to a specified thickness, removes glue extrusions, and ensures a satisfactory surface for the application of veneer. In constructing a lumber core panel, note that a sheet of face veneer, unglued, is put in place, then a sheet of core veneer glued both sides, then the lumber core, then a sheet of double glued veneer, then 2 sheets of face veneer. One is the back for the piece just completed. The other is the face for the next panel. Veneer plywood can be simply a face sheet, a core at right angles to the face, and a back with the grain parallel to the face. These 3-ply panels are placed between smooth aluminum panels known as cauls before being loaded into the hot press to be formed into 3-ply flat panels. When the press cycle is completed and the press opens, the cauls and panels are removed. The veneer panels are removed to cool and cure, and the cauls are stacked for reuse. After the press is unloaded, the press openings are loaded, each with 2 cauls containing plywood panels. The length of the press cycle is determined by the type of panel being processed. Curved plywood panels are laid up and formed by being cured between male and female molds under heat and pressure. This press also uses radio frequency energy to generate heat and cure the glue bond. In a matter of minutes, several pieces of veneer and an adhesive are transformed into a high-quality furniture part. Hardwood veneer plywood can also be made with a particle board core. Here panels are being cut to size. To minimize waste, required sizes may be special ordered or panel breakdown must be carefully planned. Particle board cores are often edge banded with lumber before the veneer surface is applied. The lumber edge can be machined, will hold screws, and can be finished to match the veneer surface. Here, lumber strips are being glued to particle board cores in a hot press. The emerging panels are separated to cool and further cure before sanding and veneering. The edge-banded panels are sanded in an abrasive planer to achieve a specified thickness and to obtain surfaces satisfactory for veneering. After the application of veneer and passage through the hot press, the veneered panels are carefully sanded to produce a finished surface. Some panels may require veneered edges as well. This machine automatically applies and trims a veneered edge on a veneered panel. The finished product is carefully examined to ensure perfect veneering. This furniture component has a built-up lumber core. Veneered on 3 surfaces, it is strong, stable, and beautiful. Since many of the specialty items produced lack only assembly and final finishing, quality control is extremely important. The final product is carefully packaged to protect its high quality. Our visit to Jamestown Plywood ends part 1 of our field trip. We have seen how softwood and hardwood veneers are produced and how softwood and hardwood plywoods are manufactured. In part 2, we will continue our trip and see how several types of panel products are manufactured and how glued laminated beams are produced. The first plant we will visit in part 2 of our field trip will be the Weyerhaeuser medium-density fiberboard plant in Moncure, North Carolina. This plant uses 35 to 40 truckloads of sawmill residue, chips, and shavings daily in the production of over 65 million square feet of medium-density fiberboard annually, most of which is used in the manufacture of furniture and cabinetry. Chips may be stored in the yard or conveyed to covered sheds to prevent wetting by rain. Upon entering the production process, the chips first pass through a powerful magnetic screen, which removes trapped metal such as nails, bits of wire, and saw teeth. The chips then enter a digester where they are steamed at 150 pounds per square inch pressure for 3 minutes. The cooked chips then pass through a refiner, which employs a stationary and a rotating pattern disc operating at close tolerances to convert the chips to fine wood fiber. These are refiner discs. After leaving the refiner, a water glue emulsion is added and the fiber glue mixture is dried in a blow tube dryer. The dried mix is stored in bins until needed in mat forming. We can get an overall look at the production line from our vantage point. First, we have the mat formers. Then a pre-press, which compresses the thick mat to ease handling. Then a trim saw, which trims the panel to width. Then a flying saw, which cuts panels to length. Then a moisture detector. Then a density monitor. Let's take a closer look at this end of the plant. The mat is laid down continuously in 3 separate layers, although the mat and final product is completely homogeneous in structure. The mat, about 4 inches thick, then passes through a pre-press, which compresses the mat to less than 1.5 inches. This makes handling the mat easier. The mat then is trimmed to slightly over 5 feet in width, and a flying saw cuts the continuous mat into length slightly over 24 feet. A metal detector detects stray metal in panels and diverts them from production into the plant fuel supply. Moisture content and mat forming are also monitored, and any defective panels are recycled into the fiber bins. Production line processes are closely monitored by both remote sensors and television monitors from control rooms at each end of the production line. Panels next enter a series of trays for temporary storage during hot press cycles. When the trays are loaded and the press opens, the press openings are simultaneously loaded and the newly pressed panels are pushed into a similar set of trays on the opposite side of the press. Panels enter the press at a moisture content from 8 to 9% and exit at about 3%. The hot press uses a combination of steam heat and radio frequency energy to cure the panel adhesive in a cycle lasting from 3 to 4 minutes. The exiting rough panels are trimmed to exact width and length and are stacked for sanding, surface treatment if needed, and shipment. Panel dimensions are frequently checked. Panels are sanded both sides and graded. The graded panels are routed to different bins depending upon grade. A separate small saw line produces small and precisely dimensioned specialty panels for other industries, such as hardwood plywood cores. Specialty items such as these door parts can be ripped from small panels. Custom sizes are produced for other industrial uses such as hardwood plywood core stock. A substantial inventory of stock and custom sizes is maintained to quickly fill customer requirements. Shipments from the plant are 80% truck and 20% by rail, with the plant having an in-plant spur. For our next plant tour, we're going to travel to Skippers, Virginia, the location of a new Georgia-Pacific-oriented strand board plant. Manufactured of wood strands layered perpendicular to each other, OSB is used in roof and sidewall sheathing and other construction applications. Low-grade logs coming into Skippers range from 11 to 55 feet in length and are a mix of southern pine and yellow poplar. With a mixture of tree length and log length material, the logs entering production first pass through an unscrambler remotely controlled. The unscrambler sorts and places the logs so they are parallel to each other and oriented properly for the deck saws, which will cut them to 100-inch lengths. After cutting to length, the blocks pass through a drum-type debarker. Holding about 8 cords, the debarker allows continuous processing of 100-inch blocks. After debarking, the logs are passed through a second saw, which is set for 100 inches, and are then passed through a set of saws, which cut them into 33-inch bolts. Bark and trimmings are conveyed away for boiler fuel. The processed bolts are conveyed to storage bins to be used as needed or conveyed directly into the plant for conversion into wood strands. The strands are chipped from the bolts, so the wood grain tends to run parallel to the long dimension of the strand. Here are a handful of strands resulting from the processing of a bolt. After chipping, the strands are then conveyed to a rotary dryer. After drying, the strands are conveyed to rotary tumblers and mixed with injected phenolic resin and a wax binder. After mixing, the material is conveyed to forming machines. The strands are oriented by fins on conveyor belts which deliver the strands to the production line conveyor. This OSB has 4 layers. The first is laid down parallel to the mat's direction of travel. Then 2 successive layers are laid down perpendicular to the first. Then a 4th layer is laid down parallel to the first. Here's how the strands are oriented in this panel. The newly formed mat is trimmed to a width of 8½ feet and a length of 24½ feet. The OSB mats are placed in the press charger one at a time while the press is closed. The loaded charger discharges an entire charge into the press, pushing the last charge out into a waiting set of trays. After loading, the press closes and the curing cycle begins. Meanwhile, the press charger is reloaded. The mat, after forming, is about 2 inches thick. After 3.5 to 4 minutes in the hot press, they are compressed to 3/4 of an inch. The press opens after the curing cycle, the newly formed mats are inserted, and the cured mats are removed. The cycle then continues and repeats. The cured mats are then removed from the tray system one at a time and proceed to a set of saws. The first set of saws cuts the 100-inch panel in half and trims the edges to produce 2 4-foot by 24-foot strips. The panels then make a left turn and are routed through a second set of saws which cut each 24-foot strip into 3 8-foot panels, producing 6 4x8 panels from the original panel. The panels are graded immediately after sewing from a grading station above the conveyor. The grader watches for surface damage and defects, defective material, broken edges, and corners. Panels are routed to appropriate bins and separated according to grade. After separation by grade, panels are sanded and, if required, edges are machined. Georgia Pacific Sturdy Floor, for example, has tongue and groove edges. The tongue and groove help maintain a level surface at panel edges when panels are used as underlayment. After sanding, the graded panels passed over an APA grading wheel, which prints the appropriate information on each panel. Some panels have their edges sealed for protection against moisture. In one of the last production steps, the Georgia Pacific logo is stenciled on the package of panels, and the package is then wrapped. Both truck and rail transportation are critical to the skipper's plant. The plant is designed to produce about 400 million square feet annually. If each panel was 3/4 inch in thickness and 4 feet by 8 feet, how high would a pile of single panels totaling 400 million square feet be? With production volume at this level, truck and rail shipments must be closely scheduled. The next panel product we'll examine is hardboard at the Georgia Pacific plant in Conway, North Carolina. This panel product is familiar as the material used in clipboards and in manufacturing pegboard. An important raw material used in the manufacture of hardboard is whole tree chips. These chips are produced as part of land clearing operations, timber thinnings, and in the cleanup of treetops and limbs following conventional logging operations. In this chipping operation, a feller buncher, using a hydraulically operated shear, severs each tree at ground level, accumulates a number of stems, and then places them in a neat pile for skidding to the chipper. A grapple-equipped skidder then moves each pile of stems directly to the chipper. The whole tree chipper processes the entire tree, bark, trunk, limbs, and leaves into chips. The chips are blown into vans which can be filled in less than 15 minutes. This chipper is powered by a 600 horsepower diesel. Units of over 1,000 horsepower are often used. The chips are transported to the mill by truck or rail. Purchases are made on a weight basis. Trucks are dumped and the chips conveyed to a screening system. A vibrating screen allows usable chips to fall through to be blown onto storage piles. Oversized chips vibrate off the screen and are re-chipped to an acceptable size before being blown onto the storage piles. Chips entering the plant are routed through a digester where chips are steamed for 5 to 7 minutes at 90 to 100 pounds pressure per square inch before passing through refiners for reduction to fiber and the injection of phenol formaldehyde resin. Fiber is then conveyed through a series of fans and collectors while drying and being delivered to mat forming machines. After mat formation, the mat passes through pre-press rolls which compress the mat prior to the pressing operation. Mats are deposited on mild steel cauls and conveyed to an accumulating cage for loading into the press. When full, the accumulator discharges into the hot press while the newly pressed boards are discharged into a cage. The press closes and the boards are cured under heat and pressure. Upon completion of the cycle, the press opens and the process continues. The pressed boards are separated from the cauls and sent through a series of cooling fans. After cooling, the newly pressed boards are stacked prior to conditioning. In the conditioning process, a rack of boards is sent through a tunnel or kiln and is subjected to heat and humidity to bring the moisture content of the panels to between 5 and 6%. This ensures the panels will be dimensionally stable in use. The panels then leave the conditioning tunnel to be unloaded from the rack and to be graded. Panels are graded by inspection of the top surface after emerging from the conditioning tunnel and are sorted into 2 grades. The graded panels are then trimmed to finished size. The trimmings are chipped and used as boiler fuel. After trimmings, graded panels are sanded to obtain a finely finished surface. Some of the plant's production passes through a perforating press, which punches 3 rows of holes simultaneously, producing pegboard. Several sizes, grades, and types of hardboard are produced at Conway, a good example of a plant manufacturing a quality product from a neglected source of raw material. The last plant we'll visit on our tour is the Unilam division of Unadilla Silo, located in Unadilla, New York, manufacturers of glued laminated beams and timbers. Incoming southern pine is carefully graded according to standards required in the production of glued laminated beams and marked for trimming. The graded lumber is trimmed automatically and is then piled according to the grade mark on each piece. The plant maintains an inventory of graded 1- and 2-inch lumber in several widths. The graded lumber enters production by first having finger joints machined in both ends. Due to the trimming of defects, lumber is random length. The finger jointing machine advances the lumber first to one end of the carrier, then to the other to permit finger jointing of both ends of the lumber. Glue is applied and the lumber is discharged to a conveyor. Finger joints are extremely strong and are used to produce a continuous length of lumber which will be cut into specific lengths according to production needs. The finger jointed stock is joined by hand. The nature of the joint makes accurate assembly very easy. After joining, the continuous length of stock passes through a radio frequency glue dryer. Emerging from the tunnel, the stock is cut to lengths dictated by production requirements. The cut-off saw is computer controlled. The stock is then surfaced 2 sides to bring the stock to a standard thickness and to remove glue extrusions in preparation for the laminating process. A finished finger joint has a very neat appearance and possesses great strength. After surfacing, the stock is put through a glue applicator and laid up into a laminated beam according to a production work order. After the laminations have been glued and assembled, clamps are assembled and carefully tightened. The assembly is clamped to ensure that the laminations are stacked correctly and that the glue joints are held under pressure. The beam we have seen assembled and clamped is a straight beam, but complex shapes and arches are routinely produced. We'll see some of these further into the production line. This jig is being assembled by bolting jig elements to the special grooves or slots in the floor, following the pattern for the arch, which will be laminated in the jig. After the glue has cured and the beam is removed from the clamping jig, straight parallel surfaces are planed to obtain a fine finish, truly parallel surfaces, and to remove glue extrusions. We can actually see the top head planing the beam's upper surface. The pattern on this beam gives one some idea of the trimming which must be done to produce a finished beam. Patterns, once used, are stored in a pattern loft. In trimming a beam to size, the pattern is securely clamped to the newly made beam. Blueprints and measurements are checked to avoid errors in the finishing of the beam. The beam is first cut to length. Surface defects are removed by routing a standard router recess in the beam to specific depth. The recess is cleaned of sawdust, glue is applied, and a router plug is tapped into the recess. The surface is planed even with the beam surface, and a scraper is used to finish the patch. Curved surfaces are first sawed to the beam's pattern and then finished with a motorized hand surfacer. Some beams and arches require the fabrication and attachment of steel fittings, one of the last steps in the production process. Some idea of the variety of shapes, simple and complex, which are made at Unadilla can be gained from the beams ready for shipment. This ends our field trip, which covered over 2,000 miles. Although we've seen a great variety of products and processes, all of them are examples of how technology has combined wood fiber, adhesives, and know-how to produce useful products.
Skills Orientation Series. Plywood Specifications and Grades. Plywood is one of the most common and important products used in construction and manufacturing. Plywood is used to build houses, cabinets, furniture, and dozens of other items. This program will show you different kinds of plywood available, what they're used for, and how to tell them apart. In short, you'll learn some plywood specifications and grades. Plywood is made from very thin layers of wood. These layers are peeled off logs at lumber mills, much like you'd peel the skin from an apple. These layers are stacked on top of each other and glued together to make sheets of plywood. Like other kinds of wood, plywood has grain. The layers of wood that make up a sheet of plywood are always placed so the grain runs at right angles to the layer above it. This technique is called cross-banding. Placing the layers in this manner makes plywood much stronger than if the grain of the layers all ran in the same direction. You can see the layers clearly if you look at the side of a piece of plywood. The grain of the top and bottom layers always runs in the same direction. This means that there will always be an odd number of layers, 3, 5, 7, or 9. The standard size of a sheet of plywood is 4 feet by 8 feet, which means 4 feet wide and 8 feet long. The thickness of plywood sheets range from 1/4 inch to 3/4 inches. Other sizes and thicknesses can be ordered, but these are the most common. All sheets of plywood have specifications and grades. The specifications are the kind and quality of materials used to make the plywood. Grades is just a short way of stating the specifications. Let's look at some of the things that make up the specifications. One specification is the plywood category. Two major categories of plywood are interior and exterior. Exterior plywood is made to be used